So today I'm pleased to introduce today's session, No Python, No Problem, Vector Database Applications with Milvus and ONNX across languages. And our guest speaker, Stefan Webb. Stefan is a developer advocate at Zilliz. He advocates for our open source vector database Milvus. And prior to this, he spent 3 years in the industry as an applied ML researcher at Twitter and Meta, collaborating with product teams to tackle their complex challenges. Stefan has a PhD from the University of Oxford and has published papers at leading machine learning conferences like NeurIPS, ICLR, and ICML. He's passionate about Gen AI and is eager to leverage his deep technical expertise to contribute to this open source community. Welcome, Stefan. Get started with your session.
Yeah, thanks so much, Sachi. Thanks for the kind introduction. And so, as Sachi mentioned, I'm a developer advocate for Milvus, the most widely adopted open source vector database. And so a big part of that is connecting with users and helping them overcome technical hurdles that they may have. So I'm really active in the Discord, Discord, sort of face-to-face meetings, etc. And so this session was actually motivated by a user's question. And so there was a question a few months back on the Discord, which was, how can I, how can I use Milvus from, I think it was Go, so the Go language, and then how to like build applications with that. And so, I looked into, my most familiar languages are Python and C# and C++, etc. But I looked into how you would go about doing this and discovered that one of the biggest challenges is actually running your models outside of Python. So Python, of course, has a lot of really good libraries for running deep neural networks. So, you've got like Python, JAX, and then on top of that, everything from like the Hugging Face set of libraries to, to interfaces to llama.cpp. So that got me sort of thinking like, oh, this could be like a useful thing to like investigate, sort of like decipher the best way to go about it, and then share what I've learned. So that was sort of like how this topic came about. And I think it just goes to show, so users' feedback is so important because we use that to like not only sort of guide how the roadmap for Milvus plays out, but also just like what we need to do to change the documentation to make it better, what would be like a useful blog post to help users, or in this case, what would be a helpful webinar topic to put on. So really grateful that we've had so much contact with our users. Okay, so let me just sort of set the scene. So I'm going to try something a bit different this time. So I'm going to be working entirely from a web browser as well as some Visual Studio Code windows. And before I share my screen and we move over there, I just wanted to sort of set the scene. So the goal, so just imagine that we're at some startup. For some reason, we can't use maybe we've prototyped a vector database application like semantic search with Milvus and the PyMilvus Python client to Milvus, and maybe like we've used Milvus Lite. But then, for whatever reason, just like this user on Discord, you're not able to use Python in production. So the question then becomes, okay, what are your options? And I could think of like at least 3 different options. So firstly, I think this is where I should start sharing my screen, and we'll go across to the web browser. Okay, so let's see. One thing I should mention to begin with is that Milvus has other client interface libraries aside from PyMilvus for Python. So if we go to the documentation, so I'm on milvus.io/docs, and I go to install SDKs. So it says here, so the current version of Milvus supports SDKs in Python, Node.js, so server-side JavaScript, the Go language, which the Discord user was inquiring about, as well as Java. And so those are just the ones that are really well supported. We also have some sort of still official, but I guess sort of like work in progress. We have an interface for Rust as well as for C#. So that's the first question. You know, what languages can I actually interface with a Milvus vector database from? So all of those languages I mentioned, these two libraries, so for Rust and C#, they may be slightly, they may need a few updates before they will work with the latest version of Milvus. So that's something that's a work in progress. So let us know, like, if this is something that you really want to happen for your project. We can sort of prioritize that. So we know that we can access Milvus through not just Python, but also server-side JavaScript, Go, and Java. Okay, so that's one piece of the puzzle solved. But then the second piece is we have to be able to, when we do a semantic search, we have to be able to encode our text or our image or whatever the input is into our vector space. And so that would, so, you know, you could be using, if you were in Python, you could be using a language like Hugging Face's sentence transformers to take your inputs, turn them into the vectors, and then pass that to the client.search to do the similarity search on the Milvus vector database. But you know, how are we going to do this in other languages? And so I guess I think the most sort of obvious way might actually be to use like a cloud inference service. So rather than doing the inference locally, you could use, whether it's like OpenAI's service or Anthropic or any of the other providers, you could use their cloud inference, their cloud embedding models to turn your inputs into the embeddings that you then look up in the vector database. But perhaps you can't use a remote service. And also, I think it's not so convenient for when you're actually constructing the vector database. Suppose you have like 10 billion vectors you want to put into your vector database. You want to be doing that in Go. You don't want to be like using like an online inference service for like 10 billion vectors. Or it might be to do with privacy or you know, security. Maybe you can't send off your inputs to like an external cloud service. So what's like the second option if you can't do an online inference service for embedding? Well, something I think sort of like a really like neat trick is to set up like a sort of a local server on your machine. So you could create very easily a like Python server that you can then send local host requests from your app to this Python server, and then the Python server runs the Hugging Face library or whatever, does that embedding locally, and then passes back the vector to your program. So I think that's sort of like a really neat way to do prototyping of vector database applications in another language. So you can do sort of like all the, you know, like the tricky deep neural network calls in Python. You know, maybe you've got some like, maybe you sort of designing your agent or whatever using the numerous Python libraries for that. But then you can just sort of call it from your program that's not in Python as like a local web service. So that's the second option. But I think, you know, that's probably not ideal always for production. So in the case of this user on Discord, they weren't able to run Python on the machine or the system that they were productionizing their application on for whatever reason. So I think, yeah, this is sort of like an interesting scenario. So we can't use an online inference service. We can't use like a Python program that we just sort of send HTTP requests to. So what are we going to do in that case? And so this is where a technology called ONNX is really useful and is sort of like the, I guess, like the main topic of this webinar. So what exactly is ONNX? Well, let me go to their website. So so ONNX, in a nutshell, so it stands for Open Neural Network Exchange. It's a like a format for representing machine learning models. So often deep neural networks, whether they're like transformers, CNNs, or, you know, just some arbitrary deep neural network. It's like a platform independent format for representing networks, and then a bunch of tools for performing inference based on that interchangeable file format. And so this is a technology that was, so, you know, it's not just like some sort of like fringe technology. It was initiated by the PyTorch team at Meta, and then it was sort of, you know, Microsoft joined, then IBM, Huawei, Intel, etc. So this is like a technology that has backing of many large players in industry. And since it was, I guess, like developed September 27, it was accepted as a graduate project in the Linux Foundation for AI and data. And so similarly, so that Milvus is also a Linux Foundation project. Actually, very similar dates. I think we sort of joined early 2020, so about the same time. So the purpose of this technology is to allow, so yeah, as it says here, to allow developers to move more easily between frameworks. So in this case, moving really easily between our Python frameworks and whatever frameworks we're using in Go or Java or JavaScript. And then secondly is, so this format, it's sort of a bit like the intermediate representation code of, you may know that, so Java is compiled to this like intermediate representation. And then there's like another step that actually turns that into the native code that runs on your machine. So it's sort of like that. So ONNX defines this intermediate representation, and then because it's I guess like hardware agnostic at that stage, different backends can then perform various optimizations on that representation specific to the platform. So for example, if your backend is NVIDIA's CUDA, then it will be able to use all of the right operations from the CUDA libraries and related ones to speed things up. Or if the backend is Apple's, I think it's called Metal, for doing ML on the M1, M2, M3 chips, then it'll be able to sort of compile to code that exploits sort of like specific operations of the Apple hardware. Okay, so okay, we sort of like discussed like what is ONNX, what is sort of like its goals, but just to make it a bit clearer. So yeah, here we go. So this intermediate representation defines a computational graph for your model. And so here's a simple example here. So in this case, they're just like writing down a linear regressor, linear regressor model, and they define a few operations and nodes, and then you can visualize this graph as in this figure here. So in this particular model, we can see that so the inputs are X, A, and B. And then there's an operator node, matmul, for matrix multiplication, which does a matrix multiplication on X and A. And so this question mark times question mark, that's because the shape, I think, is being left undefined in the graph, but you could also fix parts of the shape. And then there's an add operation. So, we take the output of that matmul and then add B, and then the output is Y. So this is a simple example of what the intermediate representation looks like for a simple linear regressor model. And so for like a deep neural network, it'll just essentially be a more complex version of this, with a transformer architecture, sort of having all these additional matrix multiplications, and should make sense like if you sort of like delved into like the mathematics of how a transformer works. But essentially, the key point is this is like a really sort of general purpose computational graph. So we can take this, so we can export this, save this to a file, and then use that file between frameworks and backends, and run the neural network across all of those different scenarios. So yeah, as it says here, so ONNX aims at providing a common language any machine learning framework can use to describe its models. And I think so primary goal was to make it easier to deploy an ML model in production. So just as in the case of this user, so they want to deploy their vector database application that has an embedding model for text in production. And so, this is like a technology that is designed for exactly that. Okay, so yeah, just a few more things before we move on. So this graph, it has input nodes, so they're special. It has output nodes, they're special. It also has like these operator nodes in between. In other cases, you can also have like initializer nodes. So obviously, like you want to sort of initialize neural network weights in many scenarios. So this is like a very simple illustration of the intermediate representation, but it has a lot more depth. It has many operations defined so that you can create, you can represent any machine learning model you can think of, essentially. Okay, so let's now go into some code. So I'm going to go across to so maybe this would be a good point to ask. Does anyone have any questions? And when I'm sharing my screen, I can't actually see the chat window. So maybe if Sachi, you could sort of chip in and just let me know if there's questions so far. Well, actually, no. Oh, okay, no, actually, I worked out how to bring up the chat window. Okay, so let's actually look at some code now, and let's see how we can go from working in a Python framework to working in Java. And so in this example, so I'm going to be showing how you can export a text embedding model from Python using Hugging Face. And then I'll show how you can then import it and perform inference in Java. Okay, so first thing, we just need to like import. Let me turn word wrap off. We need to import our libraries. Oh, by the way, is this font size large enough for everyone? Let me know if not, I can adjust. Okay, so we import so the ONNX library, ONNX runtime. It's going to be using NumPy to represent matrices, and then we'll be using the sentence transformer library from Hugging Face. So when I was sort of like working through this, I discovered there's a lot of like gotchas at the moment, because this partly because this is still like a technology that is like under rapid development and developing like a wider user base. So here's my first attempt, and then I'll show you the gotcha, and then I'll show you like the workaround. So the first attempt was, so what I'll do is I'll use sentence transformer to load this this all mini LM sentence embedding model from the Hugging Face model hub. And it turns out that, so on the Hugging Face model hub, all of those models have already been converted to ONNX format. So I'm going to go across now. Let's see. Yeah, here we go. So this is the model card page for that same model. And you can see that there's a folder called ONNX. And I click on that, and you can see that it has various files for different versions of the model. So model.onnx, presumably that's just sort of like the plain sort of conversion of the PyTorch model to ONNX. And then we have 01 to 04 for different levels of optimizations applied to the graph. Optimizations that are not hardware specific. And then we have some ones that looks like they're sort of like defining like an 8-bit precision, as well as having some specializations to specific platforms. Okay, so my first attempt was, let's just load that into memory, and then save it using the export optimized ONNX model function from the sentence transformers library. So I load the model, so download from Hugging Face, load the model, and then I run this function here to export that model to like a file. And then, so I can use the ONNX library, that's the one that you would use to sort of do like graph operations. So you can check that the graph is valid. You can take one graph and another graph and combine them. You can do all sorts of things like that. So firstly, I think it's just a good idea. Let's check that the model is a valid graph. So I load it up with this onix.load, and then I run the model checker on top of that. And if it gives back none, that means that the graph is okay. Okay, so that's all good. So let's take a look at the graph and see what the input nodes and the output nodes are. I use, again, the ONNX library, and I use just sort of like accessing this attribute of the graph object in Python. So .graph.input, and .graph.output. And then for each of those nodes, I extract the name. And so we see that, so for this file that's been converted already is on the Hugging Face model hub. The inputs are the input IDs. So these are the token IDs. So remember that before you actually run the embedding model, you have to tokenize your text. You have to take the string, break it up into small chunks, typically words and subwords, and then convert those to the corresponding token ID for that model and tokenizer. So this will already expect the token IDs. There'll be an attention mask. So maybe we want to, so for example, if we have padding, we may need to pad all of our sequences so that they're the same length. And then we can use this attention mask to let the model know that it should only perform the calculations on the number of tokens that are not padding. And then there's this token type IDs. So that's a bit miscellaneous. So you can look into that if you're interested. So, okay, that looks good. So, but what about this output? So the output is the last hidden state. Okay, so now we have a bit of a problem because we want the output to be the embedding. But the last hidden state is not the embedding. So a few things have to happen before we actually have calculated the embedding. So so how a lot of these sentence embedding models work is they take a language model, like a language encoder. So for example, BERT. So let's look at, BERT. Yeah, okay. So I'll just open up this image in a new tab. Okay, yeah, so here's like an illustration of BERT. So BERT is like a transformer, like an encoder style transformer model. It takes a sequence of tokens and then outputs for each token like a context dependent embedding. But we want like a single embedding for the string. So how like these sentence embedding models typically work is they take the output from all of the outputs, so one embedding per token, and then they perform some sort of like a pooling operation. So it could be just like averaging all of these outputs. It could be taking the maximum over all the dimensions. I think sort of like in maybe like rare cases, you could just take like the first one or the last one. And then you may also want to do like a normalization on that embedding vector after that. So yeah, so it looks like we've got a bit of a problem because the file we downloaded from Hugging Face, it will give us like these final outputs, but it doesn't look like it's defining the pooling function as well. And so if we look at how sentence transformers actually works, we can see that for each of these models, it has a modules.json file. And so these like define sort of like a number of steps that define like how we go from the tokens to the sentence embedding. So the 0th step is a transformer. So that's i.e. like this diagram here is that 0th step. But then the 2nd step is pooling. And this pooling operation, it's defined within sentence transformers. I think it's going to be using like an average. Might actually be in one of the configuration files here. I think it's just using the fact that the default pooling function is taking the mean. And then finally, it takes the pooling and then applies like a normalization to it. So I think, yeah, just sort of like looking into this, sort of had to like delve a bit deeper into how sentence transformers is actually working, and some details of how we produce these text embeddings. So yeah, so we've discovered like a bit of a gotcha. We won't be able to just just run this one line and then export ONNX and then have like a model that we can use in Java or Go or C# or whatever. So that's our first attempt. So as I've written here, so the ONNX model from sentence transformers, it doesn't include the pooling and normalization modules, which is a problem. So let's look at some other, let's sort of try something different. So essentially, we need to use another library that sort of knows that sentence transformers models have multiple modules, and then it will sort of do the right thing by using all three of them. So actually, reading that modules .json file, and then using that to actually construct the full PyTorch model that's then exported. Maybe let's look at attempt 1.5. So we can actually also directly export a model from PyTorch. So we can load up the embedding model as we did before, but now we're not calling backend equals we're not calling backend equals ONNX. So we're actually going to load the the standard weights from the sentence transformers model hub page on Hugging Face. And yeah, okay, so we can see that we can then sort of use this function from PyTorch, torch.onnx.export, and then we give it an nn.module, so like a PyTorch model with learnable parameters, and then some other parameters like defining the input/output, and that will return an ONNX model that we can then save. But to actually to do this for a sentence transformers library, we would have to write some additional code that reads the modules JSON file, parses it, and then uses that to call the appropriate, construct the appropriate PyTorch modules, and then saves them to a single graph. So I think we don't want to do that ourselves if someone's already done it for us. And so that's why we should look at using some other libraries for this purpose. And so there's one library called Optimum, which is part of Hugging Face, and it has a command line utility that you can use to export a model to ONNX format. You install the Optimum package, pip install Optimum, and then you can run this optimum-CLI command line instruction, and then we do export ONNX model. Then we give like a name to the Hugging Face, where it's located on the Hugging Face model hub, as well as the file name. And so this code behind the scenes, it knows that these models have multiple modules, and it knows the right thing to do. I found an easier library to use was this one from text.ai. So you can see this is like a common issue if different parties have been developing libraries to do the same thing. So I installed this library from text.ai, and then they have a module text.ai.pipeline, and then Hugging Face ONNX. And so this will sort of take care of all of those things for us. So I give it the model name. I create this HF ONNX object, and then I just pass in the path. And yeah, so I tell it the task is pooling, so i.e. Outputting text embeddings. So if you just wanted like the context dependent embeddings, like maybe you're using like a late interaction style paradigm, so like Cole Pally, then you could replace that with the appropriate type of task. Okay, so we when we do it this way, we now have a model that we've run this code. We'll load that ONNX file back into memory. We'll check the graph, so the graph looks good. Now let's look at the inputs and the outputs. Okay, so the inputs, we've got the input IDs of the tokens, the attention mask, token type IDs, so that's the same as last time, so that's all good. But now the output is embeddings, as opposed to last hidden state. So now this is exactly what we want. So now when we call this ONNX model, we will get the text embeddings. And then we can take that and we can use that to like insert data into our vector database, as well as embed queries to perform similarity searches. Okay, so that's one sort of like challenge that, you know, we've sort of solved that problem. But the next problem is tokenization. So before we can actually call this model, we need to convert our text to token IDs. And so that's very simple in Python, of course. When we load these models from Hugging Face, from sentence transformers, we have this .tokenizer object that automatically gets loaded. There's a lot of like just like configuration in the model hub that defines the tokenizer. So I think this JSON file, I think that has the vocabulary, and then there's like a config that sort of defines special tokens. So this is like very easy using our sort of standard Python libraries, but we won't have access to this when we move across to Java or Go or whatever. So what are we going to do here? Well, I looked at, I think there's like a few different solutions here. And so let me just sort of like tell you about the ones that I didn't do first that might, you might want to sort of go that route, and then I'll talk about the one that I investigated. So yeah, so a lot of these sentence embedding models, they have like very standard deep learning architectures. So like very sort of standard tokenizers. Often the tokenizer can be used across several models, just with a different vocabulary, some different settings. And so there's a good chance that you'll be able to find an open source implementation for the tokenizer that you need native to that language. Or you might find one that is implemented in C++ or Rust, which you can then compile as a library and then call that function, call that library from your other language like Java. That's one option. The second option is you could just implement it yourself. So it might be, I don't know, like a 2-day task, understand how the tokenizer works, and then actually sort of like implement the tokenizer in Java. But there's a third option, and that is to actually use ONNX for the tokenizer as well. Let's look at how we would do that. So it turns out that the basic ONNX library doesn't define the right types of operations to perform tokenization. So Microsoft, sort of like seeing this as like a problem that many users must be having, they created an additional library called ONNX runtime extensions. So let me yeah, so ONNX runtime extensions, it's a specialized pre and post-processing library for ONNX runtime. So in our case, we're doing pre-processing of text. We're turning the text into numerical tokens. But I think this can also do things on images, like other sort of very common pre and post processing operations. So this library will allow us to also export our tokenizer as an ONNX file, and then load that up and call that using the same ONNX runtime API. So let's see how we would go. So yeah, I think we've got maybe like about another 10 minutes left. I'll see. We should be able to get through to the end goal. Okay. So the way how we use this is we import this ONNX runtime extensions Python library, and then we just use one function that does exactly what we want it to do, which is take a tokenizer from Python, from Hugging Face, and then turn that into an ONNX function. So, okay, so we import this gen processing models, and we then call it with the tokenizer. So we've just looked inside this sentence transformers object to get the tokenizer. We've passed it to this function, and then it will return both the encoder for the tokenizer as well as the decoder. Of course, like we're only interested in the encoder in this case because we're using this as a sentence embedding model. Okay, so and then to save that as an ONNX file, all we need to do is essentially just call this serialized to string and save it to a file. And then once we've done that, well, I think it's just interesting to sort of like, yeah, just sort of like check that it works. So I've got some code here, actually sort of like testing, making sure that this works. So, okay, so at this stage, we have two ONNX files. We have the ONNX for the model, as well as the ONNX file for the tokenizer. So let's just like check that these work in Python, and then we can move across to Java. So we'll import these libraries. So the way how you use an ONNX model is you create an inference session, and then you can call run on that inference session. So we create an inference session on the tokenizer. Really importantly, we have to register these custom operations. And so these are the custom operations from ONNX runtime extension that allow us to do tokenizers in ONNX. And then, so I've got like a test string here. So the quick brown fox jumps over the lazy dog. And then, so we call run. It turns out that the input node for this tokenizer is just called text. So we pass in that string, and then we look at the outputs, and we have this list of 4 entries. And so it turns out that, so this first one is the list of token IDs. So this is the result of tokenizing that string. And then we have, it turns out this one here is the attention mask. This one here, I think, defines the token IDs. And this one here defines like the spans of the string corresponding to the individual tokens. So, yeah. So I can then just sort of assign those to some variables. So, you know, just to like sort of verify that this is working, I'm now going to take the output of this ONNX tokenizer and then decode it using the Hugging Face tokenizer. So I'll take this output, so test tokens, I'll then put it through the Hugging Face model, and this is what it decodes it to. So you can see that it's decoded it to the same thing as the input, except that it's got like these special start and finish tokens in there. Okay, so now we've used ONNX to tokenize our string. Now let's use ONNX to calculate our embedding. And for that, we just start another inference session on the model. So you can combine graphs from different models. I wasn't able to do it. What that would mean is you could just like combine the tokenizer and the embedding model into a single graph, and then you could just feed it the text and then output the embedding. I wasn't able to do that because these two models have different versions, intermediate representation versions, and so I wasn't able to sort of like convert them to the same version to be able to make them compatible. So we'll create a second session just for the embedding model. We'll then call run, and we give it the test tokens. We give it, so I had these defined around the other way before. So it says token type IDs, but it should actually be attention mask, and vice versa here. And then the output of that is the sentence embedding. So this is the 384 dimensional sentence embedding for this particular sentence. But we've done it in a way that will work across different languages and frameworks. Okay, so just for fun, let's just like do a few different strings, see what the similarity is. So I've got the quick brown fox jumps over the lazy dog, a fast wolf leaps over the sedentary hound, and then the cat sat on the mat. And so as you can see, as we would expect, the so this is the similarity from the Hugging Face library, and then this is the similarity from the ONNX library, and you can see like the numbers sort of more or less agree. So I think the weights that we've loaded for the Hugging Face library and the weights that we use for the ONNX library are not necessarily like the same weights. They may have used like a different checkpoint, so we're not going to get like exactly the same numerical values for the embeddings, but they should sort of be like consistent in terms of similarity. Okay, so we've sort of like accomplished our goal in Python. Let's now go across and do that within Java. So Java has interfaces to both ONNX as well as Milvus. So I'm using Gradle to put together my Java application. So I just add these, I think they're called references to the to these libraries, to the Milvus SDK for Java, as well as the ONNX runtime. And then here's my main function. And so I create a session, create session options. I then create the session for the model. So here I sort of like manually entered the tokens in for the particular example. So the quick brown fox, the lazy dog. There's a bit more sort of like back boiler code working in ONNX in other languages. So I have to convert these it's like native or like sort of more fundamental Java types into ONNX tensors, and then convert that into like a dictionary from the input node name to the argument, and then I call session run. So I run the session on these inputs, and then I get back. I ask it to return the embeddings, and then have a bit more sort of boilerplate code to like extract the first 16 elements of that sentence embedding. And I'm not sure if people can see it, but I'll just copy and paste. Yeah, so these are the first several numbers from the embedding that we calculated within Java, just using these ONNX files that are platform independent. One more minute, Sachi, and then we can move across to questions. But if we go down here, so this is the output from using the same ONNX model in Python. And if you just compare the numbers, they're identical. So we've got 1.463 times 10 to the minus 1. Okay, that looks like it's that number. 3.285. Yep, 3.285. So what you can see is we've been able to calculate embeddings using the same model across Python and Java, which means that we can create our database in Python, insert those embeddings using Python, and then access them from Java. Or we could even do like everything within Java. We could create the vector database in Java, enter all of that data using this model, and then also be able to embed our query and perform a similarity search. So I think we've got a few minutes left for questions. Should we open up to questions?
Yeah, Stefan. It looks like you don't. No one asked a question yet, but if you have any questions, please put it in the Q&A tool. I think it's really interesting that Stefan was really engaging with the community on Discord, so this topic came into play. So if you are interested in joining our Discord, I've put that resource in the chat. That's where people have conversations about these things. We can do a webinar if you have a question that other people also have. So please join that. We love to see the community there. So I'm going to ask you a quick question here. So what are the key advantages of using ONNX as opposed to other inference libraries?
Yeah, sure. So, well, I think the first one is just like this sort of like cross-platform compatibility. Our model is saved to a file. We can then copy that file across networks, countries, whatever, and that will be the same model. So then the person on the other end, whatever library, so whatever language they're using, they can get the same output. So firstly, like this interoperability. I think secondly, the fact that we can develop specialized backends. So because we have an intermediate representation, so I mean, sort of similar to like you might have heard of the LLVM compiler. Because we have a single intermediate representation, then NVIDIA, they can work on their CUDA backend, Apple can work on their Metal backend, AMD on theirs, etc. So they can develop their backends independently and like very specialized to optimize to that platform. But still, it's the same ONNX file. So whether someone has like a CUDA card or whether they have like a MacBook Pro like I do, you'll be able to run it and take advantage of those platform-specific optimizations.
You have a question. Can you discuss input types and output formats for each model or library you discussed?
Yeah, sure. What we did was we loaded a PyTorch model using the sentence transformers library from Hugging Face. And so that model sort of like defined what the input types and the output types were. So there were two parts. There was the tokenizer and then the embedding model. And so the input for the tokenizer was a list of strings, and the output was like a NumPy array of the token IDs. So, but that's just defined by like how it's implemented in PyTorch. And then the embedding model, its input was those three different NumPy arrays: the token IDs, the attention mask, and the token type IDs. how I actually found that out was you can inspect the ONNX graph and you can say, print out all the names of the input nodes, print out all of the names of the output nodes, as well as their types. That type information is contained in the ONNX graph, and you can inspect it, and so that you know like the right syntax to use when you're doing your inference. Hopefully that's helpful. Okay.
So
Oh,
we are at time
yeah.
here. So thank you all. Thank you, Stefan, for your talk, and thank you all for joining. We appreciate you joining us today. The resources for this webinar and also the recording will be sent out shortly. And yeah, I hope everyone has a good rest of their day or night, wherever you're joining us from.
Okay, thanks everyone for attending.
Thank you. Bye.